Hello everyone, this video is going to be about the review of the harmonic motion of a spring lab analysis guide, particularly the graphs and the discussion that's needed because of maybe I didn't get to your group or you're just using this as additional review. So our first graph, or our first objective, we've looked at before in our Hooke's Law lab. Your graph should look something like this. It definitely is a linear relationship where the slope is your spring constant. So I don't think there's any further discussion needed, but I do want to note that there is or should not be a 0, mark because there is some minimal force needed to displace all of our springs that we've been looking at in this lab. For objective 2, I think I got around to most groups, but just in case I didn't again, this is what our graph should look like. Some groups wound up getting something that was initially maybe a positive linear slope. But if you look at your graph, and this was assuming that you did it on a computer, your scale is probably zoomed in for your period or your vertical y-axis. But if we change that scaling so that we start at some 0 mark and maybe go, I don't know, to 2 seconds, it changes the shape of our graph. And we're going to look at more of a horizontal line, which the slope of a horizontal line is 0, which that slope value is the relationship between our x and y axes, or in this case, amplitude and period. So since the slope is 0, there is no relationship. So as amplitude increases, there is no result of changing period. So we would just say there's simply no relationship there. And we won't need to include that in any equations that we derive. Moving on to objective 3. In some of my classes, this experiment, these two variables, mass and period, proved to be difficult to look at because a lot of groups did get a linear trend. And when for some of the groups, we did that R-squared value, basically that fit test. It showed up to be more linear, but it's not actually supposed to be linear. But if we did some more testing and we spent some more time, collected a lot more data, I think we would get a more of a curve there. Something like this. Or something else that we can do is say, have that discussion of if you did have no mass, no hanging mass on the spring, and you displaced it, you pulled it down some amplitude and let go, there would be no period. It would not oscillate. It would not return back to where you let it go. So this experiment would actually have a 0 mark, which for a lot of your data, even if you did have that kind of linear trend here, would show more of a curve. So that might be something to consider. And we did have a discussion, if this graph actually continued to the right, it would flatten out a little bit more, so that can kind of support some of your data that might look like it's definitely linear. So now, how do we fix this? And by fix, I mean, how do we understand it? Because we only have an algebraic understanding of the world in this course, so we need to linearize this graph. So we've done this before in way back in the beginning of the year with acceleration, and then when we looked at circular motion. So since we have this curve, it kind of shows exponential change. So one way to fix it is to square our y-axis. So if we went and looked at all of our data, squared it, regraphed it, it should come out with a linear line. And then we have mass again down here. So looking at the slope, rise over run, really we don't know what that is, a second per kilogram. What we're really looking at here is the relationship between the mass, not the number, or discovering like what the slope represents. So all we can say is that period squared is proportional to mass. That symbol, that little squiggly line, is the symbol for being proportional, or you can do this little thing that I call fishy thing. Either one would represent proportional. It's not exactly equals because there's other things that might be going on to impact the period. Another way to write this would be to say period is proportional to the square root of mass. And that's it. So we'll come back to that in a few moments. In objective 4, very similar to objective 3, a lot of groups were getting a linear trend, but notice that this is a negative trend. It would be an inverse relationship. But what this graph should look like, something like this, an upward facing curve to the right. And again, if you're not changing your independent variable all that much, you're not going to expect that much of a change. So how do we linearize this? So similar to before, we have a curve. So don't draw this part. If we graph the period squared versus the k value, that would linearize it. But something we saw when we did circular motion is we want to keep everything as similar as possible. So we don't want to have one relationship being proportional and one inversely proportional. So we want to try and get this to be a positive slope. So to get this have a positive slope, we would graph the inverse. So I'm going to erase this. The inverse of the spring constant, and that would linearize it. So again, squaring the period makes our line straight, and graphing the inverse of our mass, or of our k value, would make it positive. So now looking at the relationship, we would do the same things we did before. Period squared is proportional to the inverse of k, or we could write it that other way too. Period squared is proportional to the square root of 1 over k. So now for objective 5, and when I mean objective 5, turn your paper over to the very back. So there's only 2 experiments that showed an impact. It was objective 3, where we said period, and I'm going to keep period by itself, just because that's what we were looking at as our dependent variable. And that was changing as the square root of mass. And then objective 4, we showed that period was changing as the square root of 1 over k. So for example, if we had 9 times the mass, right, we had 9 times greater mass, the period would only be 3 times greater. And similarly with the k value. So we're trying to develop an equation here. So can we combine these terms? Sure we can. We can make this statement because we know that the period is changing by both the mass and the spring constant. So is this our equation? Can we change this proportional sign to an equal sign? The only way to tell would be to go back in our data and see if the numbers match up. So if you go into any experiment, whether it was objective 4, 3, or for our purposes, I'm going to do 2 because I already had some information here. And we're going to look at, it could be any trial, it could be any objective except for one. And we're going to look at our values and see if that equation holds true. So we don't know if this is true yet. And I'm just going to erase some of our graph here so I have some space. So we're trying to see if we could say this. We don't know if this is true yet. So we have a period here of 0.42 seconds, and I just made up these numbers. And I take the square root of my mass. And you'll do this too. You can do it for one or several trials if you want to just kind of double check. And my spring constant. So when I do this, and I plug it in, I get that these do not equal each other. Okay, so not the end of the world. We do know mass and spring constant have an effect on the period, but there's something else that we're missing. So how off are we? If we just simply figure out the ratio or divide 0.42 by 0.067, we find that that is about 6.3 times off. Meaning we need a number in our equation, or to make an equation, we're missing a variable or multiple variables. Now, if it was 9.8, that would be pretty cool because we could say, oh, we just multiply it by gravity for some reason. But it's not. It's about 6.3. So depending upon which trial you used, if your data was accurate or not, you might get around 4 or 7 or 5 or 6. But if we do this enough times, we'll get it around to be 6.3, or even better yet, 6.28 to be a little bit more precise. So what number do we know that is around 6.23, or 28 rather? So if you think back to one of the videos that you watched the other day, we related harmonic motion to circular motion. So is there anything in circular motion that would maybe play a role here and be around 6.28? So if you thought of 2 pi, you are correct. 2 pi is equal to 6.28. So if we go back to our objective 5, we can make our equation an actual equation, and this is the period or harmonic motion of a spring. This is our resulting formula, or equation rather. So make sure you understand all of the objectives. If there's any questions, feel free to send me a message or two. But I do want you turning in the lab. And I would expect on the back of your paper, on Objective 5, this area that I did, I would like to see that you copy these proportions and equation down so that I know that you watched the video, and it's a good reminder of how we came up with that equation for future labs and also in reviewing. Have a good day.